Remember when we had an inscribed polygon, it was a polygon that has its vertices on a circle. Likewise, an inscribed angle is an angle that has its vertices on the circle and its sides are contained in chords of the circle. For instance, in our example, vertex B is on the side of the circle, okay, and AB and CB are chords of the circle. Therefore, if we have a point, a second point here of D, we can say that arc ADC is the arc intercepted by ABC. There's a couple different cases that we can talk about for inscribed angles. Let's say that we have a circle with O as our origin, and if we have an angle in which, a chord in which it goes through this side of the center goes through the side, and we'll call this chord A, B, and then we have a second chord going to B, that tells us that we have the inscribed angle of ABC. Our second case is if we have our origin on the interior of the angle, and in this case we would have our vertex of B surrounding or lying in between our two chords of AB and BC. And our third case is if it's in the exterior of the angle. So for instance, we have O, and then we have our vertex of B and our chords C and A lying to the outside of the origin. So just to recap, our intercepted angle would be the angle of between the two chords, and our intercepted arc is the outside segment, the arc of the segment on the circle in between our two chords. Which leads us to a great theorem of the inscribed angle theorem, that if an angle is inscribed in the circle, then the measure of the angle is equal to 1/2 the measure of its intercepted arc. So if we have angle A, or chord AB and chord AC with a point of D on our intercepted arc, therefore we can say that the measure of angle ABC, meaning our intercepted arc, okay, is equal to 1/2 the measure of arc ADC. And then the converse is also going to be true, so that we can say that 2 times the measure of angle ABC is going to be equal to the measure of our arc ADC. Our next theorem tells us that if 2 inscribed angles of a circle intercept congruent arcs, or the same arc, then the angles are congruent. So for instance, in this example, we have that the angle ABC and angle ADC are intercepting our arc AC. Therefore, that tells us that the angle of ABC is going to be congruent to the angle of ADC. It also tells us that if we have a special triangle or inscribed polygon of where our inscribed angle intercepts a semicircle, the angle is going to be a right triangle. So for instance, we have, let's call this point A, and we have S here. Since it goes through the center, our chord goes through the center and is the diameter, we know that we have a semicircle from A to S. Therefore, our chord at AC, if we draw another chord connecting C to S, this angle here is going to be a right angle, which creates ACS as a right triangle. And our last theorem tells us that if a quadrilateral is inscribed in a circle, then the opposite angles are supplementary. So for instance, we have quadrilateral ABCD. That means that our angle B and angle D, since they are opposite, are going to equal 180, and angle A and angle C, as they are opposite, is going to equal 180, which makes sense because we know that the angle measure of all four of our angles are going to equal 360 degrees.